Our planetary neighbor is a cold, dry world, its weak gravity retaining only a thin atmosphere. As robotic probes began visiting the red planet, a more accurate picture of its surface emerged, and scientists started to wonder if Mars had once been much warmer. Evidence hinted that it possessed rivers and, in its early history, might have been able to sustain life. A succession of new technologies has since been deployed to unlock the secrets of this world. And while our knowledge of Martian geology, its atmosphere, and its weather has grown immensely, each new mission seems to raise more questions than it answers. The fundamental uncertainty remains. We still do not know if Mars has ever been a home to life. This modern inquiry traces its origins to 1877, when astronomer Giovanni Schiaparelli created what he considered the most precise map of Mars yet drawn. On it, he illustrated features he called canals. In the early 20th century, this idea captivated American astronomer Percival Lowell, who was convinced the canals were evidence of a civilization on the red planet, which began the earnest search for life on Mars. In 1962, the Soviet Union sent the first probe, Mars M1, on a flyby mission. It was an audacious project, and it failed, becoming the first of many such failures by both the Soviet Union and the United States. Cold War rivalry provided the powerful motivation for these early missions. In 1971, NASA sent Mariner 9 to Mars, and it became the first probe to orbit another planet. Scientists discovered, however, that Mars was completely enveloped in a planetary dust storm, and the initial on-orbit photography revealed little beyond a featureless red cloud. Mariner 9 was soon joined by two Soviet orbiters, both of which were equipped with landers. The Mars 2 lander crashed upon arrival, but the Mars 3 lander made it to the surface intact. It managed to return one garbled image, and then ceased to function. Mars now had 3 orbiting spacecraft, all observing a dusty, indistinct planet. Though the two Soviet probes were identical, the American probe had one key design difference. While the Soviet orbiters began photographing the planet based on predetermined schedules, NASA was able to command Mariner 9 to simply wait, hoping the dust would eventually settle. It took months for the atmosphere to clear, but when it did, Mariner 9 saw 3 craters protruding above the dust. They were the tops of giant volcanoes on what was named the Tharsis Plateau. Soon, more complex geological features began to emerge. In some places, the surface was heavily cratered, suggesting the tectonic forces that constantly renew Earth's surface were absent on Mars. The volcanic activity that built the solar system's largest volcanoes had stopped billions of years ago. This new information enabled NASA scientists to compile an accurate global map of Mars and to decide upon landing sites for the Viking probes that followed in 1976. The Viking 1 and Viking 2 missions were identical orbiters, with landers that both made successful landings on the surface. Both returned pictures of the Martian landscape. The primary objective of the Viking program was to find signatures of life, but researchers now feel the 3 experiments tasked with this analysis had significant limitations. As researchers on Earth began looking for traces of life in extreme environments, they started to rethink where life on Mars might survive. Yet, the consensus at the time was that Mars was sterile, and the idea of life on Mars effectively died. Following a 20-year hiatus in Mars research, Mars Global Surveyor went into orbit in 1996. The pictures it relayed back were clearer than anything yet seen from the red planet. Although most Mars orbiters had been tasked with mapping the planet's surface, this was different. The high-resolution images that the Mars Global Surveyor sent back revealed rivers and even river deltas. What is intriguing is that the occasional impact crater suggested that nothing has flowed in these systems for billions of years. In July 1997, another probe arrived. The Mars Pathfinder was one of a new breed of missions being pushed by NASA's new administrator under the guiding philosophy of faster, better, cheaper. The idea was to cut development times and budgets and although the risk of failure would rise, the reduced price tag could mean more missions. Pathfinder would land a small rover on the surface, and to do this, it used radically new airbag technology. The technique drew more from automotive safety systems than from previous space missions. The landing site in Mars's northern hemisphere, known as Ares Vallis, is one of the planet's rockiest areas, yet it was thought to be a safe area to land. The broad array of different rock types are believed to have been deposited during an ancient flood. The new landing technique worked perfectly and served as a proof of concept that would be used on future missions. The Pathfinder lander consisted of a base station equipped with 3 solar panels that unfolded like petals. There were sensors to measure atmospheric pressure, air temperature, and wind speed, as well as a transmitter to communicate with Earth. In addition, Pathfinder acted as a base station for the Sojourner rover that explored the surrounding area. Sojourner was fitted with cameras and an alpha particle X-ray spectrometer. It was the first mission to have its own website. The rover returned thousands of images and important detail about the atmosphere and geology, and its popularity guaranteed more Mars missions. On the morning of April 7, 2001, another Mars orbiter was launched. Mars Odyssey was equipped with 3 primary instruments, and it had the ability to act as a relay satellite between future surface missions to the Red Planet and Earth. On its arrival at Mars, it used a new technique to go into orbit. After firing a relatively brief pulse of its engine, Mars Odyssey went into a highly elliptical orbit that at its closest approach had it skimming the planet's thin upper atmosphere. Called aerobraking, this technique allowed the craft to circularize its orbit over a period of 3 months, and it saved around 200 kilograms of fuel. The probe is still in operation today, breaking all records as the longest-serving Mars mission. In December 2003, a new player arrived at Mars. The European Space Agency, using a Russian launcher, had sent Mars Express, its first planetary explorer. It was equipped with a lander known as Beagle 2, though all contact was lost with the lander. Mars Express, however, continues to return valuable data. The mission has been granted several extensions, the latest till 2020. Fitted with a high-resolution stereo camera, the Mars Express probe delivered uniquely detailed 3-dimensional views of the planet's terrain. The orbiter's observations also determined that the polar ice caps were not uniform, but instead a composite of frozen carbon dioxide and water ice. Within the thin Martian atmosphere, the mission made a series of compelling discoveries, first detecting methane and later ammonia. The presence of these gases was particularly intriguing because both break down quickly under solar radiation, which implied that some active source on Mars must be constantly replenishing them. While inorganic processes can occasionally produce methane and ammonia, their existence is more commonly linked to biological activity. Just a month after Mars Express settled into its orbit, a new phase of exploration began as a NASA lander reached the Red Planet, with a second, identical craft following only 3 weeks behind. These were the Mars exploration rovers, given the names Spirit and Opportunity. Spirit, arriving first, was aimed for the vast Gusev crater, while Opportunity's destination was Meridiani Planum, on the opposite side of the planet. Despite being significantly more massive than the earlier Pathfinder mission, they employed the same innovative airbag-cushioned landing method. Both rovers achieved precise and successful touchdowns. Once a craft came to a rest and oriented itself, it separated from its landing platform and initiated an autonomous sequence, carefully unfurling its solar arrays and raising its camera mast. Back on Earth, the team at the Jet Propulsion Laboratory endured a tense wait, as the radio signals that would confirm a safe arrival required a full 15 minutes to cross the expanse between the two worlds. For many on the team, this moment was the culmination of years of dedicated work, yet it marked only the very beginning of the mission's true purpose. The 2 rovers were initially engineered for a mission lasting just 90 Martian days. To avoid confusion with Earth time, the science team adopted the term Sol to refer to a single solar day on Mars, which is approximately 40 minutes longer than our own. Mission planners had anticipated that the planet's notorious dust storms would gradually coat the rover's solar panels, eventually cutting off their power. However, an unexpected benefit of the Martian climate emerged. The local winds were consistently blowing the panels clean. Before long, NASA shared a landmark discovery from Opportunity, which had found compelling evidence that liquid water once existed on the surface. Images from Meridiani Planum revealed stratified rock patterns, a clear indicator of ancient sedimentation. Further analysis of chlorine and bromine distribution in the area provided chemical clues that this site was once the shoreline of a salty sea. In light of these findings and the rover's robust health, NASA announced in April 2004 that their missions would be extended from 3 to 8 months, a decision that would be the first of many such extensions. Each rover carried a rock abrasion tool designed to grind into the outer surface of a stone to allow for a more detailed analysis of the uncontaminated geology beneath. This capability was used for the very first time by Spirit on a rock in Gusev crater designated Adirondack, marking a significant first in the field of planetary geology. The decision to use the tool was not taken lightly by researchers, as the process placed a considerable strain on the rover's limited power reserves. The analysis revealed the rock was composed of olivine, pyroxene, and magnetite, a composition remarkably similar to volcanic basalt found on Earth. Later in its mission, Spirit's right front wheel ceased to function. In response, engineers on the ground worked with a duplicate rover to develop an unconventional driving technique, allowing Spirit to move in reverse while dragging the immobilized wheel. This action inadvertently created a deep furrow in the Martian soil, which serendipitously exposed a new subject for scientific inquiry. Within the trench, the science team observed white and yellow deposits, identified as various salts, that typically form only in the presence of hot water. On our own planet, such hydrothermal environments are known to support microbial life. Spirit continued its journey for another 3 years, before its wheels became irrevocably trapped in soft sand. Once again, engineers tried to solve the problem using a replica on Earth, placing it in an identical predicament, but no solution could be found to extricate the rover. Spirit was then reclassified as a stationary research platform. Even subsequent efforts to tilt the rover for better solar panel efficiency were unsuccessful, and the final transmission from Spirit was received in March 2010. Its twin, Opportunity, would go on to operate until June 2018, its mission finally ending when a planet-encircling dust storm obscured its solar panels. Meanwhile, a new chapter in orbital observation began in March 2006 with the arrival of NASA's Mars Reconnaissance Orbiter. The spacecraft initiated the now standard procedure of aerobraking, using the friction of the upper atmosphere to carefully shape its orbit. While this process took nearly 6 months to complete, the significant fuel savings are projected to allow the craft to remain operational well into the 2030 seconds. A critical role for this new orbiter is to serve as a powerful communications relay for surface missions. Its 3-meter antenna, transmitting in the ultra-high frequency band, facilitates exceptionally high rates of data transfer. The impact was profound. By November 2013, the orbiter had already relayed more than triple the amount of data sent back to Earth by all previous NASA missions combined. The high-resolution camera aboard the orbiter began to reveal the Martian surface with breathtaking clarity. The images captured dynamic processes in action, such as active, cascading dunes inside East Coprates Chasma. They showed the polar regions as they emerged from their seasonal covering of dry ice, revealing vast fields of surrounding dunes, and documented unusual pits forming in the southern hemisphere's residual cap of carbon dioxide. The poles of Mars were becoming a focus of intense scientific interest, guided by NASA's prevailing exploration mantra, follow the water. The Phoenix lander was specifically directed to the northern polar region, its mission designed to investigate data from the Mars Odyssey orbiter that pointed to large deposits of frozen water just below the surface. Because orbital imaging showed the landing area to be relatively uniform, a mobile rover was considered unnecessary. For its descent, the lander was engineered to use a parachute for initial deceleration, followed by rocket thrusters for a soft touchdown, a departure from the airbag system used by the 3 prior NASA rovers. This design choice sparked some debate, as one line of research raised concerns that the rocket exhaust could potentially contaminate the very soil samples the lander was sent to analyze. After touching down, the craft paused for 15 minutes, a deliberate wait to let any disturbed dust settle before it unfurled its solar panels. Phoenix arrived during the early spring of the Martian northern hemisphere, ensuring its solar arrays would get abundant sunlight for the mission, which was planned to last for 90 days. In addition to its camera mast, Phoenix carried a meteorological station to record daily weather patterns, complete with a wind indicator as well as pressure and temperature sensors. A particularly novel instrument was a vertically aimed LiDAR, which for the first time observed the formation of cirrus clouds and even detected snow falling through the polar atmosphere. The lander was also furnished with a robotic arm, capable of digging half a meter deep into the ground. This arm could then deliver soil samples to an onboard analyzer, which consisted of 8 high-temperature ovens paired with a mass spectrometer. During one excavation, the lander's cameras captured images of a white substance in the trench that slowly vanished over several days. Considering the ambient temperatures and the duration of its disappearance, the science team concluded it could only be water ice, which sublimated directly into vapor once uncovered. The soil analysis brought mixed news for the search for life. It was found to be slightly alkaline and contained perchlorate, a chemical compound that is harmful to bacteria. Phoenix ultimately functioned for 2 months beyond its primary mission, until the advancing winter sun dipped too low, leaving its solar panels in permanent shadow. The mission confirmed that while the surface may be arid, the planet still held vast subterranean deposits of ice. While little water remained on the surface, the evidence now suggested that many of the red planet's features were carved by liquid flows. Analyses from across Mars affirmed that water alone was responsible for these transformations. The planet had once resembled Earth before losing its surface water and most of its atmosphere, leaving a persistent question about life. Could it have emerged in that warmer past? And could it endure underground? NASA's next mission, its most ambitious yet, was the car-sized rover Curiosity. A nuclear battery would power it, avoiding the dust issues that plagued Spirit and Opportunity. Curiosity launched from Cape Canaveral in November 2011 aboard an Atlas V. In the middle of 2012, after its main engines had ignited and carried it from Earth, a sophisticated craft pierced the thin Martian atmosphere. Its target, the vast floor of Gale crater, at the Jet Propulsion Laboratory, mission controllers closely observed the autonomous entry, though they held no direct influence over the sequence of events unfolding millions of miles away. Mars's tenuous atmosphere meant that the large parachute alone could only reduce the heavy vehicle's speed to approximately 320 kilometers per hour. As it drew closer to the ground, the rover's descent stage separated from the protective aeroshell, and a series of powerful rockets ignited to provide the final braking. During this critical phase, radar systems guided the lander toward the surface, while a small camera captured images of the terrain passing below. The rover, named Curiosity, was then gently lowered from the descent stage on a set of tethers. This innovative sky crane technique was specifically designed to prevent the rocket engines from blasting the landing zone with swirling dust, which could have exposed the rover to unnecessary risk. The entire complex maneuver had functioned with flawless precision, bringing immense relief to the American engineering teams who confirmed that the landing had been the most accurate ever achieved on another world. Before Curiosity could embark on its mission, its onboard computer systematically worked through an exhaustive checklist, a crucial step to ensure all of its intricate systems were functioning correctly after the arduous journey. A full day passed on the Martian surface before the rover received commands to deploy its high-resolution camera mast and its vital communications antennas. It is thought that Gale crater itself is a remnant of an ancient impact from around 3.5 billion years ago, and its deep layers of sediment are believed to have been deposited first by flowing water and later by persistent winds. With Curiosity's arrival, NASA now had an advanced mobile science laboratory on the Red Planet, connected to Earth through a high-bandwidth communications link provided by the Mars Reconnaissance Orbiter. The rover's fundamental objective is to determine if conditions suitable for life ever arose, or perhaps might still exist, on Mars. In addition, it is meticulously gathering detailed information about the planet's current environment, with a particular focus on measuring the radiation levels that will be a critical consideration for any proposed human missions in the future. Over the course of its exploration, Curiosity has analyzed the fine dust from a number of holes it has drilled into the Martian rock. These samples revealed the presence of sulfur, nitrogen, hydrogen, oxygen, phosphorus, and carbon, a collection of elements that are all considered essential building blocks for life as we know it. In its 6 years operating on the surface of Mars, the rover has journeyed approximately 20 kilometers, but the difficult driving conditions have clearly taken a toll. It regularly transmits a series of self-portraits back to Earth, which serve mainly as a way for engineers to perform diagnostic checks on its condition. These images show that its wheels have sustained severe damage from the rugged landscape, an observation that will undoubtedly inform significant design changes for the next generation of planetary rovers. Its computer systems are also beginning to show signs of age, but a new suite of missions slated to arrive at Mars in 2020 will carry on the important work of profiling the planet. There is one particular aspect of the Martian environment that had never been investigated before, a scientific question that a new mission was designed to address. The Mars Insight probe was specifically targeted to land on the flat, expansive plains of Elysium Planitia, a region situated near the planet's equator. Its purpose is to spend 2 years carefully investigating the planet's deep interior, a place of profound mystery. The probe executed a perfect landing in November 2018, and after successfully unfurling its large solar arrays, it spent several weeks meticulously surveying its immediate surroundings. It was searching for a suitable spot to deploy a highly sensitive seismometer onto the surface, an instrument designed to listen for faint tremors or Marsquakes. It has become clear that Mars once had a much warmer and wetter past, but today it is a cold and exceptionally dry world. Learning more about the planet's ongoing geological activity will provide crucial clues that help us understand precisely why Mars changed so dramatically over time. The InSight probe also carried another key instrument, a thermal sensor that it hammered deep into the surface to gather data on the flow of heat escaping from the planet's core. By developing a clearer understanding of the processes occurring deep within Mars, scientists hope to learn how the geological histories of our own world and the Red Planet first began to diverge. Far out in the solar system lies the ringed planet, Saturn, a world with more than 100 times the mass of Earth. Its dense, metallic core is buried beneath an enormous 80,000-kilometer deep ocean of liquid hydrogen and helium, which is why it is classified as a gas giant. This majestic planet is orbited by a diverse family of at least 62 moons, each one a unique world unto itself, with some possessing remarkably complex and dynamic environments. Our only detailed, up-close examination of the Saturnian system concluded in 2017, when the Cassini probe was intentionally commanded to crash into the planet's dense atmosphere. This final act was a protective measure, designed to eliminate any possibility of accidentally contaminating Saturn's pristine moons with earthly microbes. When viewed from Earth, Saturn's iconic rings are visible, but they appear without any significant detail. For a long time, they were thought to be solid, continuous structures, until careful mathematical analysis suggested they were actually composed of countless individual particles orbiting the planet. This raised fundamental questions about how these rings formed and why Saturn alone among the known planets appeared to possess such a magnificent feature. In the early days of space research, Saturn was simply too far away to reach. The conventional rockets of the era possessed just enough power to send small probes to Mars, leaving the outer solar system well beyond their grasp. Then, in 1964, NASA scientists realized that a space probe launched in 1977 could take advantage of a rare alignment of the outer planets. This unique orbital configuration would allow a spacecraft to fly past all the gas giants, using a series of gravitational assists from the planets themselves to propel it onward. With the technology available at the time, such a mission would be just barely possible. From this insight, an ambitious new undertaking began to take shape, and it was soon given the fitting name, the Grand Tour. The plan involved 2 probes that were far more advanced than anything that had been attempted before, which were to be part of the ongoing Mariner series of spacecraft. However, because no vehicle had ever been sent beyond the orbit of Mars, mission planners felt it would be prudent to first send 2 more rudimentary probes to Jupiter and Saturn. These advanced scouts would test the conditions of the deep space environment. Researchers were particularly concerned about the asteroid belt located between Mars and Jupiter, and they did not know if it was even possible for a spacecraft to safely cross it. In 1972, Pioneer 10 was launched on a trajectory toward Jupiter, and the following year, its twin, Pioneer 11, was sent on a path that would eventually take it to Saturn. Both of these small craft passed by Jupiter successfully, and in the process discovered that the electron radiation in its vicinity was an astonishing 10,000 times stronger than what is found at Earth. This was a complete surprise to the engineers at NASA, who then had to modify the more sophisticated craft they were preparing for the Grand Tour to better withstand this harsh environment. The probes being constructed at NASA's Jet Propulsion Laboratory were originally part of a program known as Mariner Jupiter-Saturn. However, this functional name was soon changed to the more inspiring title of the Voyager program. The 2 Voyager spacecraft were launched just 16 days apart in the late summer of 1977. By this time, Pioneer 10 was already heading toward interstellar space, and Pioneer 11 was still 2 years away from its own encounter with Saturn. In 1979, as Pioneer 11 approached the ringed planet, it began to send back pictures that were far clearer than anything that had been seen before. A previously unknown ring, which was named the F ring, was observed for the very first time. The craft's trajectory was designed to fly by Saturn, passing just beneath the plane of its rings. Mission planners were uncertain about how broadly the ring particles were spread, and if there was a threat to the spacecraft, they were fully prepared to sacrifice Pioneer 11's order to get a clear idea of the environment that the subsequent Voyager craft would encounter. The small probe passed the rings safely and continued on its journey beyond Saturn, heading out into the vastness of interstellar space. NASA received its final communication from the trailblazing probe on the 24th of November, 1995. The Voyager 1 and 2 probes were constructed with exceptional durability, engineered for a profoundly long mission, and outfitted with technical abilities that far surpassed the earlier Pioneer spacecraft. As late 1980 arrived, Voyager 1 made its approach to Saturn. Although its high-resolution polarimeter was no longer functional, the probe still managed to discern a previously unknown ring, designated the G ring, which circled the planet 100,000 kilometers above its cloud tops. For the very first time, mission scientists could observe the dynamics of the rings themselves. One of the more curious discoveries involved uneven features that appeared to move within the rings, which were named spokes. These are understood to be transient phenomena, believed to consist of particles elevated by an electrostatic charge. After such a long period of preparation, the sheer volume of information arriving at the Jet Propulsion Laboratory was overwhelming for the planetary scientists. The moons of Saturn were a subject of intense curiosity, and Voyager 1's trajectory had been specifically plotted to allow for a close pass of Titan, which is the second largest moon in the solar system and the only one known to possess a substantial atmosphere. The resulting images, however, were a source of disappointment, as the moon's thick haze of methane and nitrogen proved to be completely impenetrable. Following its encounter, Voyager 1's path carried it up and out of the plane of the solar system, setting it on a course that would eventually lead into interstellar space. A final, parting glance back at Saturn captured one last image from an entirely unique perspective. Nearly 10 months passed before Voyager 2 drew near Saturn. Its distinct trajectory was designed to allow it to continue onward to Uranus, and then Neptune. The craft's high-definition camera remained operational, and researchers were anticipating highly detailed photographs of the rings. They were not let down. The variations in density and spacing throughout the ring system were more intricate than anyone had foreseen. The rings are identified by letters of the alphabet, assigned in the order of their discovery. It also became clear that the rings had undergone changes in the interval since Voyager 1 had observed them. While they extend from 7,000 to 80,000 kilometers above Saturn's equator, their average thickness is a mere 30 meters. The spacecraft also sent back images of the moon Enceladus, revealing a cracked, uncratered surface composed of ice, beneath which lies a vast ocean. Ultimately, Voyager 2 departed Saturn, unable to enter orbit, and accelerated toward Uranus. A period of 23 years would elapse before another probe would visit the ringed planet. That mission began with the 1997 liftoff of the Cassini spacecraft, an ambitious collaboration between NASA, the European Space Agency, and the Italian Space Agency. Its journey to Saturn would take more than 6 years. Cassini represented the largest and most complex interplanetary vehicle ever conceived. It carried 12 distinct scientific instruments, each supported by a dedicated team of research specialists on Earth, who would interpret the data it transmitted. Its high-gain antenna served as the primary conduit for high-speed data relays back home, but it also had a secondary function. During what is known as a ram maneuver, it could be used as a shield, protecting the spacecraft from debris impacts, a particularly vital capability when crossing the plane of Saturn's rings. On the 1st of July, 2004, Cassini fired its engine to achieve orbit around Saturn. The entire system was engineered for reliability. Alongside its main engine was a complete backup, ready in the event of a primary engine failure. It was also equipped with 16 monopropellant thrusters, 8 primary and 8 more for redundancy. Back in mission control at the Jet Propulsion Laboratory, engineers were temporarily blind to the events unfolding millions of kilometers away. The significant time delay, combined with Cassini's disappearance behind Saturn, meant that much of the telemetry was recorded on board for later transmission to Earth. The critical engine burn lasted for 106 minutes. Cassini was also the first probe to utilize a solid-state recorder, a significant advancement over the mechanical tape recorders used by the earlier Voyager craft. Cassini's initial orbit was a highly elliptical path designed to carry it out past the moon Titan. This trajectory was crucial for 2 distinct reasons. First, Titan's gravitational pull was necessary to modify Cassini's course over time, enabling observations of Saturn and its other moons from a wide array of perspectives. Second, Titan itself, with its dense atmosphere, was a primary target of investigation for the Cassini team. To this end, the European Space Agency had constructed a smaller craft called Huygens, which was attached to Cassini's side. During the second approach to Titan, the Huygens probe was released. It was outfitted with a heat shield, a parachute, and enough battery power to operate for several weeks. Over a 20-day period, Huygens drifted across 4 million kilometers of space. 3 days after separation, Cassini performed a course correction to ensure it would not collide with Titan. As Huygens began its entry into Titan's atmosphere, Cassini was swinging around for its third close flyby of the Moon, positioning itself to receive the signals from the lander. The probe successfully sampled the atmosphere and captured images of the terrain below. These pictures from beneath the clouds unveiled a landscape of low hills and channels that had been cut by flowing liquid. There were very few impact craters, and those that were present showed signs of heavy erosion. This marked the first successful landing on a celestial body in the outer solar system. Images taken from the surface depicted weathered rocks composed of water ice. The great surprise for everyone involved was the revelation that Titan is a geologically active world, where liquid, ethane and methane, rather than water, have sculpted the surface features. As Cassini continued its long, looping orbits around Titan, it employed radar to map the Moon's surface, confirming the widespread presence of hydrocarbon lakes. The probe's observations established that rain does fall on Titan, but it is a mixture of liquid ethane and methane. The Moon possesses weather and other erosional forces similar to those on Earth, but its fundamental chemistry is radically different. Elsewhere in the Saturnian system, the small moon Enceladus began to draw significant attention. It stood out as the whitest, most reflective body in the solar system. Its surface displayed cratering in the northern regions, but its southern hemisphere was marked by giant cracks known as tiger stripes. During Cassini's first pass of Enceladus, the magnetometer team observed a peculiar deflection in Saturn's magnetic field, almost as if the small moon had its own atmosphere. On the second pass, the team noted the same phenomenon. They subsequently requested that the next traverse of Enceladus be much closer, and Cassini's course was adjusted to fly just 175 kilometers above the icy moon. On this pass, the probe flew directly through a plume of water vapor that was emanating from the tiger stripes. Analysis revealed that the vapor contained common salt. In total, Cassini made 24 swoops past Enceladus, with the closest approach bringing it just 25 kilometers above the surface. With each pass, the probe's various instruments gathered different lines of evidence about the jets of water being expelled through the cracks in the Moon's southern pole. While rovers on Mars had been meticulously combing the surface for traces of life, Enceladus was actively broadcasting remarkable signs of its own. Gravitational analysis uncovered the existence of a liquid ocean beneath the ice, and infrared detectors registered heat radiating from the cracks. In addition to salt, the science team later discovered traces of silica within the plumes. The material venting from Enceladus also contained hydrogen and organic compounds, substances which would only dissolve in warm water. Data from the Cassini probe had already established that a global ocean exists on this moon, confirming the presence of water. Furthermore, organics were directly measured in both the gaseous and particulate matter of the plumes. A source of energy was also confirmed. The South Polar region was significantly warmer than the rest of the Moon. This led to the discovery of evidence for hydrothermal vents deep on the seafloor of Enceladus. Such vents could provide both the heat and the chemical nutrients that might be capable of sustaining life. With a diameter of only 500 kilometers, Enceladus is considered far too small to maintain a hot core through internal radioactive decay. While the constant gravitational flexing from Saturn can account for some of this warmth, the ultimate source of the high temperatures observed remains an unresolved question. The situation is intriguing because not only is there liquid water beneath the ice, but there is also organic material and a source of heat. When scientists consider the potential for life to emerge elsewhere in our solar system, they look for 4 essential ingredients. A heat source, liquid water, and organic material are the first 3, and the fourth is the stability of those 3 conditions over a vast period of time. long enough for life to potentially arise. On Enceladus, we have found the first three, but the long-term stability of its environment is not yet known. On Earth, hydrothermal vents in the deepest parts of the ocean provide the warmth and nutrients to sustain entire ecosystems, and some theories suggest they were critical for the very origin of life itself. For this reason, many planetary biologists now speculate that the ocean environment of Enceladus may represent the most probable location in the entire solar system to find some form of extraterrestrial life. It took a considerable amount of time for Cassini to maneuver into a position where the sun's backlighting would allow the imaging team to capture photographs of the plumes. Employing a similar observational geometry, the team acquired a remarkable image, with Saturn positioned directly between the spacecraft and the Sun. This unique vantage point revealed Saturn's E-ring, a diffuse and hazy outer ring that is typically very challenging to observe. The E-ring is a direct consequence of the plumes erupting from Enceladus, and it is constantly being replenished by these saltwater emissions. Stating that Saturn has 62 moons can be somewhat misleading, as in principle, any particle within the ring system could be classified as a moon. The system is incredibly diverse, containing inner large moons and outer large moons. There are shepherd moons that sculpt the edges of the rings, co-orbitants that periodically swap their orbital paths, and even moons that orbit other moons. Each one is a unique world. During the earlier Voyager missions, the study of these moons was almost an afterthought. For the Cassini mission, however, a close and detailed examination of the moons was a central objective from the very beginning. Iapetus circles Saturn in an orbit beyond that of Titan. It was first seen in 1671 by Giovanni Cassini, who noticed it as a point of light when it was to the west of Saturn, but found he could not see it when it should have been on the eastern side. The reason for this is that Iapetus has one brilliantly bright hemisphere and one profoundly dark one. Because the moon is tidally locked with Saturn, its dark face is always the one leading the way in its orbit. One prominent theory proposes that this surface is darkened by sweeping up a constant stream of debris that is ejected from Phoebe, a more distant moon. Another feature of Iapetus has left scientists puzzled: a massive ridge that runs along its equator, stretching more than halfway around the moon. This ridge is twice the height of Earth's tallest mountain. On a world that is only 1,500 kilometers across, this equatorial feature gives Iapetus the distinct appearance of a walnut. Extremely precise and carefully directed bursts from Cassini's main engine gave mission engineers the ability to modify the probe's looping orbits around the planet. This flexibility allowed mission specialists to focus their instruments on various moons, different regions of the ring system, or specific parts of Saturn itself. By using gravitational assistance from the moons, particularly the massive Titan, mission control was able to conserve significant amounts of fuel. The Cassini probe performed its tasks so flawlessly that it was granted 2 mission extensions, but its fuel supply could not last indefinitely. The mission planners had always scheduled the most hazardous phase of Cassini's journey for its final year at Saturn. In late 2016, Cassini initiated a series of polar orbits that would carry it close to the outer edge of the rings, a maneuver the mission specialists referred to as grazing on the rings. The spacecraft's mass spectrometer and its cosmic dust analyzer were tasked with sampling particles and gases as it repeatedly crossed the ring plane. During orbit 251, its first pass above Saturn's North Pole, it recorded the strange hexagonal storm that was first hinted at in images from the Voyager probes. The storm, which is more than twice the diameter of our own planet, has maintained its hexagonal shape, but its color has shifted with the arrival of summer in the northern hemisphere. At its center lies a vast cyclone, shown here in false color, where red indicates lower clouds and green represents higher ones. The winds at the storm's edge blow at an astonishing 540 kilometers per hour. One component of Cassini's dual-technique magnetometer had ceased to function early in the mission. Without it, the spacecraft had to perform periodic roll maneuvers in order to properly calibrate the instrument. The flight plan called for the spacecraft to complete 20 of these ring-grazing orbits, with the work of its various instruments choreographed down to the second. As the Sun moved to a position almost directly behind the rings, Cassini searched for evidence of dust clouds, which would suggest some unknown process is actively grinding ring particles down into a fine powder. Cassini also conducted a number of radio occultation observations, which involved positioning the rings between the spacecraft and Earth. 3 separate radio signals, each with a different wavelength, were transmitted at the same time, allowing the radio science team to construct a detailed profile of the ring particles. This false color image of the A-ring, the outermost of the large, bright rings, shows particles larger than 5 centimeters across in red. Green denotes particles smaller than 5 centimeters, while blue represents particles smaller than 1 centimeter. The intricate gravitational interplay between Saturn, its rings, and its many moons results in the formation of gaps at very specific locations. Before Cassini's arrival, only 18 moons were known to orbit the planet. By the end of its mission, that number had grown to 62. The delicate structure of Saturn's F-ring is maintained by a pair of small shepherd moons, Prometheus and Pandora. Prometheus patrols the ring's interior boundary, while Pandora orbits along its outer edge, and their combined gravitational influence carefully corrals the ring particles into a narrow, confined stream. In April 2017, the Cassini mission entered its final, dramatic phase, with its trajectory altered to send the probe on a series of passes inside the rings themselves. While this new path would inevitably end with the spacecraft burning up in Saturn's atmosphere, the scientific return was deemed invaluable. The data gathered from such close proximity would provide an unparalleled understanding of the gas giant. Mission planners concluded that a controlled destruction of Cassini was the responsible choice, far preferable to the risk of leaving a derelict craft to drift and potentially contaminate one of Saturn's pristine moons. As it dove closer, Cassini's instruments detected a surprising phenomenon, a constant influx of ring material raining down onto the planet. This continuous shower consists of ice and dust, with some particles pulled by gravity toward Saturn's equator, while others, carrying an electric charge, spiral down along magnetic field lines at higher latitudes. The sheer volume of this ring rain is astonishing, with an estimated 10,000 kilograms of material falling onto the planet every second. At this observed rate, the entirety of Saturn's magnificent rings could vanish completely within 100 million years. Researchers also made the unexpected discovery of an electric current connecting the innermost D-ring to the planet's upper atmosphere. During its final, close encounters with Saturn, the spacecraft began to skim the very top of the atmosphere. With all previously collected information secured on its recorders, Cassini started transmitting its findings directly back to Earth in real time. This final act required the constant firing of the spacecraft's thrusters to prevent it from tumbling, ensuring its high-gain antenna remained precisely aimed. The probe's last tasks involved sampling the composition of the atmosphere and measuring the offset of Saturn's magnetic axis. Back at mission control, there was nothing more the engineers could do but watch the incoming signals, which had been sent from the distant planet 84 minutes earlier. Within 45 seconds, the spacecraft itself would be gone, leaving behind a legacy of data that will take years to fully analyze. As of now, no future missions to Saturn are scheduled. Jupiter stands as the largest planet in our solar system, containing more than double the mass of all the other planets combined. Its atmosphere is a turbulent tapestry of swirling bands moving at different speeds, and its great red spot is understood to be a storm of immense proportions that has persisted for centuries. Yet, recent imagery from a new probe flying over Jupiter's poles has unveiled a world that looks entirely different from these familiar views. To the ancient Romans, Jupiter was the celestial embodiment of their king of the gods. In 1610, Galileo Galilei, using a newly refined telescope, observed moons orbiting the planet, providing clear evidence that not everything in the heavens revolved around Earth as was commonly believed. Although increasingly powerful telescopes improved our perspective, a truly clear look at Jupiter remained elusive until 1964. It was then that Gary Flandreau, a graduate student working at NASA's Jet Propulsion Laboratory, made a critical discovery. By charting the future positions of the outer planets, he identified a rare alignment that would occur in 1977, enabling a single spacecraft to visit Jupiter, Saturn, Uranus, and Neptune in sequence. NASA quickly seized upon this extraordinary opportunity, initiating work on twin probes for what was then called the Planetary Grand Tour. To minimize risks for the more complex missions to follow, two simpler spacecraft, Pioneer 10 and 11, were rapidly constructed. Their purpose was to fly ahead and gather information about the interplanetary environment on the way to Jupiter. Pioneer 10 launched in March 1972, becoming the first craft to successfully traverse the asteroid belt between Mars and Jupiter. Because it was also the first human-made object set on a course to leave the solar system, it carried a small plaque indicating its terrestrial origins. By December 1973, Pioneer 10 was transmitting images of Jupiter that were sharper than any seen before. As it neared the giant planet, the probe encountered an intense radiation field, with iron particle levels 10,000 times stronger than those in Earth's own radiation belts. When the spacecraft skimmed past Jupiter, it experienced a significant acceleration. Having left Earth at a speed of 51,000 kilometers per hour, its velocity more than doubled upon its departure from the gas giant. This gravitational slingshot effect was the key principle that made the entire Grand Tour possible. The Grand Tour craft, which had been renamed Voyager 1 and 2, were being prepared for launch at Cape Canaveral when the data on Jupiter's harsh radiation environment arrived. The intense electron radiation had triggered false commands aboard Pioneer 10, a serious concern for the far more sophisticated Voyager probes. In a remarkable last-minute improvisation, local supermarkets were cleared of their kitchen-grade aluminum foil. This foil was then used to shield critical electronic cables on the Voyager spacecraft. Without this simple but crucial modification, electrical pressures reaching 40,000 volts could have been induced in the probe's subsystems during their Jupiter flyby. Voyager 2 was launched in August 1977 on a trajectory that would allow it to visit Jupiter, Saturn, Uranus, and Neptune. 16 days later, Voyager 1 departed on a different, faster path that would permit flybys of only Jupiter and Saturn, along with several of their largest moons. At the time of their launch, the Voyager probes were the most advanced robotic explorers ever built. Because they would be operating at such vast distances from the Sun, solar panels were not a viable power source. Instead, they were outfitted with radioisotope thermoelectric generators, which harnessed the heat produced by the natural decay of plutonium-238 to generate electricity. As Voyager 1 approached Jupiter in January 1979, it began returning sequences of images that revealed a planet of incredible complexity and dynamism. The planet's great red spot, long a subject of fascination, was finally seen for what it was: a colossal rotating storm system. In 1665, Giovanni Cassini had noted a permanent spot on Jupiter, which was observed intermittently through the 1700s. It wasn't until the late 1800s that the feature was described as being red, and it remains uncertain whether these historical sightings refer to the same storm we see today or to a recurring atmospheric phenomenon. Voyager 1 made its closest pass of the giant planet in early March 1979, forever changing our view of this distant world. As the Voyager probes neared Jupiter, activity at NASA's Jet Propulsion Laboratory would swell into periods of intense focus, a stark contrast to the long, quiet transits between planets. These brief flyby windows, would unleash a deluge of information that often overwhelmed the research teams. Perhaps the most profound legacy of the Voyager missions was how they completely reshaped our view of the Galilean moons. What had once been mere points of light in telescopes were revealed to be four unique and fascinatingly different worlds. The innermost moon, Io, offered the first major shock with its sulfurous, yellow-hued surface. A long-exposure image captured a strange plume, revealing that Io was not a frozen, inactive body, but a geologically dynamic world. The immense gravitational pull from Jupiter constantly flexes Io's interior, generating enough heat to power massive volcanic eruptions that hurl material hundreds of kilometers into space. 3 months after Voyager 1's pass, its twin spacecraft made its closest approach in July 1979, providing an opportunity to study different moons more closely. The next revelation came from Europa, a world distinguished by its high reflectivity and the smoothest surface known in the solar system. Images showed long pressure ridges strikingly similar to ice flows in Earth's polar regions, suggesting Europa was a frozen world with a vast liquid ocean hidden beneath a thick ice shell, its internal warmth also generated by tidal forces. As Voyager 2 journeyed onward towards Saturn, planetary scientists were left with a treasure trove of raw data that would take years to fully process. While the twin spacecraft had provided the first detailed portrait of the Jovian system, they had also uncovered more mysteries than they could solve, and more than a decade would pass before another terrestrial probe would visit. That next visitor was the Ulysses spacecraft, launched aboard the Space Shuttle Discovery in October 1990 with a primary mission to investigate the Sun's polar regions. To achieve this goal, the European-built probe needed to leave the ecliptic, the relatively flat plane where all the planets orbit, a remnant of the primordial disk that formed our solar system. The mission's ingenious solution was to use Jupiter's powerful gravity to slingshot Ulysses out of this plane and into a unique north-south solar orbit. Ulysses was not alone in leveraging this gravitational advantage. The Cassini mission to Saturn, which began in 1997, and the New Horizons probe to Pluto, launched in 2006, both used Jupiter flybys to dramatically shorten their long voyages while gathering valuable scientific data as they passed. Meanwhile, inside the cleanrooms at the Jet Propulsion Laboratory, a new kind of Jupiter mission was being developed. This spacecraft, named Galileo, was designed to be the very first to enter into orbit around the planet for long-term study, featuring a large 4.8-meter antenna designed to be folded during launch and unfurled once safely on its trajectory. The Galileo mission faced significant delays. Though its launch was initially planned for 1986, the tragic explosion of the Space Shuttle Challenger forced the probe into storage for several years. It finally embarked on its journey in October 1989, carried into space by the Space Shuttle Atlantis. Following the launch of Atlantis, a change in the rules governing shuttle missions dictated a new plan for propelling Galileo out of Earth's gravity. The spacecraft was now mandated to use a less powerful solid-fuel upper stage, a shift that required a completely different trajectory. Instead of a direct path, Galileo was sent inward toward Venus to perform a gravity assist maneuver. This new flight plan, however, meant the spacecraft would have to endure a much hotter part of the solar system. As a precaution, it was decided the large, heat-sensitive main antenna would remain furled and protected until after the probe looped back on a course past Earth. To build up enough velocity for its journey, Galileo made 2 separate close passes of our planet. The first of these flybys occurred in December 1990, over a year after it first left Earth. When it returned for its second pass another year later, the mission team attempted to deploy the high-gain antenna, but it opened only partially. After months of trying various techniques to unstick the mechanism, engineers reached a difficult conclusion. They believed that long-term storage had caused essential lubricant at the tips of the antenna's ribs to dissipate, preventing a full deployment. The consequence was that researchers would have to rely on Galileo's much smaller secondary antenna, which meant data would be delivered at significantly slower rates for the entire mission. During its long cruise toward Jupiter, Galileo's path took it past several asteroids. One of these was a body named Ida, which provided a remarkable discovery. It was the first asteroid ever observed to have its own moon, a small companion, later named Dactyl. In July 1995, while still 6 months from its ultimate destination, Galileo released a small, separate probe. This probe was designed to plunge directly into Jupiter's atmosphere and sample its chemical makeup. It survived for about an hour in the turbulent environment, relaying its findings back to the main Galileo spacecraft, which recorded the data for later transmission to Earth. The analysis of this information yielded several surprises. The probe detected hardly any water vapor, which was contrary to expectations, and other elements, most notably helium, were present at far lower concentrations than models had predicted. The probe also passed through areas of extreme heat and cold, a pattern suggesting that a great deal of heat is being released from deep within the planet's interior. A little more than an hour after the final transmission from the probe was received, Galileo began its crucial orbit insertion burn. Its main engine had to fire continuously for 49 minutes to slow the craft enough to be captured by Jupiter's gravity, settling it into a highly elliptical, equatorial orbit. This initial orbit was designed to be altered later with another engine burn at its highest point. Mission designers were keenly aware of the intense radiation environment around the planet, and this second burn was intended to lift Galileo's closest approach higher, above the most extreme radiation zones. On that first orbit, which eventually brought the spacecraft near Ganymede, Jupiter's largest moon, engineers were also trying to diagnose damage to the vital onboard tape recorder. Without the high-gain antenna, this recorder was absolutely essential for storing data from brief, high-speed encounters with the moons, which could then be played back slowly to Earth. The device had become stuck in rewind mode for 15 hours, and a section of the tape had been degraded. The investigation revealed that light-emitting diodes, which were key components in the recorder's control system, had suffered defects from radiation exposure. The second orbit also included a pass of Ganymede, where Galileo made an extraordinary discovery. It is the only moon in our solar system that generates a significant magnetic field. The data also indicated the presence of a vast ocean, sandwiched between two distinct layers of ice. Galileo's subsequent orbits were slightly varied, allowing for close approaches to Jupiter's other major moons. However, the equatorial paths needed to reach these moons also repeatedly took the spacecraft through dangerous hotspots in Jupiter's radiation belts. Based on earlier observations from the Voyager missions, the moon Europa was a target of special interest for the Galileo team. Data gathered from several of the spacecraft's instruments confirmed that a salty ocean does indeed exist beneath Europa's icy surface. A later, more detailed examination of the Galileo datasets uncovered information from its plasma wave and magnetic field instruments showing that plumes of water vapor were actively erupting from cracks in the moon's surface. Europa holds more water than all of Earth's oceans combined, making it a compelling location in the search for extraterrestrial life. The moon Io was already known for its volcanic activity, but Galileo revealed the sheer scale of the forces at work. It detected tides in the moon's solid surface that rose and fell by more than 100 meters. The immense heat generated by this constant gravitational distortion of Io's crust makes its numerous volcanoes hotter than anything found on Earth. Over the course of its 8 years at Jupiter, Galileo successfully completed 35 orbits, profoundly deepening our limited understanding of the Jovian system. It was never an easy mission. While Galileo was a robustly built spacecraft, the harsh radiation environment placed immense strain on all of its subsystems. Engineers on the ground were in a constant state of finding workarounds for the frequent breakdowns the spacecraft suffered. Instruments showed increased levels of noise when near Jupiter, and current leakages caused by radiation led to several resets of the onboard computer, resulting in the crucial loss of data. Eventually, software changes were uploaded that enabled the computer to recognize these resets and recover on its own. The information learned from these challenges would directly lead to changes in how the next spacecraft to Jupiter was designed. That new chapter began on August 2011, with the launch of an Atlas V rocket carrying the Juno probe on a track to Jupiter. Juno embarked on a journey that would last for almost 5 years, and its mission parameters were fundamentally different from Galileo's. It was designed to ignore the moons and focus exclusively on the planet itself. The spacecraft's design reflected the lessons learned, with its crucial electronics shielded inside a thick titanium vault. And rather than using a plutonium power source, Juno would rely entirely on solar panels. The intensity of sunlight at Jupiter is only about 5% of what it is at Earth, so the panels had to be enormous. This change in power source was driven by a shortage in the available stocks of plutonium-238. Juno followed a long, looping orbit that first took it out beyond the orbit of Mars, before it swooped back toward Earth for a gravitational boost. This flyby added 14,000 kilometers per hour to its velocity, sending it on its final path to Jupiter. The probe approached Jupiter on a trajectory that carried it high above the planet's north pole. It was destined for a north-south polar orbit, a path specifically chosen to keep it beneath the most severe sections of the planet's radiation belts, which extend outward from Jupiter's equator. 4 days before its closest approach, Mission Control sent a command that initiated the spacecraft's autopilot sequence. Then, on July 4, 2016, Juno began the engine burn that would insert it into an initial 53-day orbit. 48 minutes later, Mission Control at JPL received a series of tones verifying that Juno had started its deceleration maneuver. This was followed by a tense 35-minute wait for the systems engineers before confirmation finally came through that Juno had performed the burn exactly as intended. For the Juno scientists and engineers, it was a profound relief that the mission was proceeding according to plan. Juno is equipped with a suite of instruments capable of penetrating deep into Jupiter's thick cloud layers. Its unique polar orbit allows the spacecraft to compile a 3-dimensional map of the upper atmosphere, building a complete picture of the entire planet as it rotates below. The images of Jupiter returned from this new perspective were stunning, appearing to come from a different world and leaving researchers amazed. The original plan was for Juno to make only 2 of these long 53-day orbits before changing to a series of much shorter 14-day orbits, which would speed up the rate of data collection. The spacecraft's main engine is fueled by a combination of hydrazine and nitrogen tetroxide, which ignites on contact. The spacecraft's propulsion system works when propellant and oxidizer are combined, a reaction which expels them using a bladder inflated by helium gas. A problem arose as Juno completed its second pass around Jupiter. The helium valves failed to operate as expected. Mission controllers made the decision to keep the probe in its existing, longer orbit, and an official extension was approved to accommodate this new trajectory. Soon after the valve malfunction, Juno entered a protective safe mode, which shut down its scientific instruments and resulted in a loss of data. While this initially seemed reminiscent of issues that plagued the Galileo mission, engineers determined the cause was a localized data transfer error from a single instrument, confirming that the spacecraft itself was otherwise in excellent health. Until the arrival of Juno, a clear view of Jupiter's poles was virtually impossible because the planet's axis has a mere 3-degree tilt. What infrared observations from the probe revealed was a striking and complex pattern of storms at each pole. At the northern pole, a primary central vortex is encircled by a formation of 8 distinct anticyclones. A similar, though not identical, arrangement exists at the southern pole, where a central storm is ringed by 5 anticyclones. The intriguing detail here is that scientists are still working to understand the dynamics that allow these powerful storms, all spinning in the same direction, to coexist so closely without merging or destroying one another. During its seventh close approach to Jupiter, Juno passed directly above the iconic Great Red Spot. This provided an unprecedented opportunity for its microwave radiometer to measure heat distribution deep inside the storm, reaching depths of 350 kilometers. The data showed that temperatures increased significantly at the lowest altitudes the instrument could probe. Unlike on Earth, where solid land masses can disrupt and weaken storms, Jupiter has no such geographic features to cause their dissipation. This may explain the storm's longevity. While the Great Red Spot has remained fixed at a latitude 22 degrees south of the equator, it has also been observed to drift entirely around the planet's circumference on at least 10 separate occasions since detailed records began. The sheer scale of Jupiter's magnetosphere is immense, creating vast bands of trapped charged particles that pose a significant threat to the sensitive electronics aboard an orbiting probe like Juno. It was long believed that this magnetic field was produced by a process similar to Earth's, known as a dynamo action, involving the motion of conductive fluid deep inside the planet. However, the information returned from Juno suggests a different origin. The uneven, lumpy characteristics of Jupiter's magnetic field seem to indicate it may be generated closer to the surface, perhaps within the atmosphere itself. Similarly, the powerful auroras seen at the planet's poles appear to be driven by a mechanism distinct from the one that creates them on Earth. By studying the gas giant's fundamental composition, researchers aim to unlock secrets about the conditions that existed when our solar system first began to form. The thinking is that while Earth has been constantly reshaped by tectonic activity, Jupiter has likely preserved its original chemical makeup from the primordial cloud of gas and dust. To conclude its scientific journey, Juno will be deliberately directed into Jupiter's atmosphere. This final act is a crucial measure of planetary protection, designed to prevent any chance of contaminating the planet's potentially life-bearing moons. The focus of the next major mission to the Jovian system will be one of those moons, Europa, which is considered the most promising candidate beyond Earth for hosting some form of life. This new probe, named Europa Clipper, was scheduled for a 2022 launch. Following Juno's example, it will rely on solar power. Its carefully planned elliptical path around Jupiter will allow it to perform a close flyby of Europa once every 2 weeks. Initial mission planning for Europa Clipper had considered including a lander component, but this concept was ultimately set aside as being premature. Before a surface landing can be attempted, much more information is needed about the conditions on the icy moon. Although Europa's ice shell is estimated to be at least 19 kilometers thick on average, precise measurements are required to map its variations. If regions with a thinner crust can be identified, they could become targets for subsequent missions designed to reach the vast liquid ocean believed to exist below. In fact, new concepts for robotic explorers capable of operating beneath the ice are already being developed, and it is likely that future exploration will also expand to Jupiter's other fascinating moons. Jupiter's role in the solar system is profound, as it is by far the largest planet, containing more than double the mass of all the other planets put together. Its immense gravitational pull influences the orbital paths of every other body in the system. While our understanding of Jupiter grows, it is worth noting that some planets have received far less attention from scientific probes. The outer ice giants, Uranus and Neptune, are exceptionally difficult to reach due to their vast distances from the Sun. Uranus is 20 times farther out than Earth, and Neptune is 30 times farther. To date, both of these worlds have only been studied up close by a single mission, NASA's Voyager 2 spacecraft. At the other extreme, Mercury presents a different kind of challenge. Its proximity to the Sun means that any spacecraft sent there must follow a complex, indirect route to counteract the Sun's powerful gravity. The planet was first visited by the Mariner 10 probe during a flyby in 1973, and later, the Messenger probe successfully entered orbit around Mercury in 2011. Venus, our nearest planetary companion, poses unique challenges for exploration, making it far more difficult to study than its proximity might suggest. A thick, impenetrable layer of cloud conceals its topography, while the conditions on its surface are utterly hostile. Early Soviet landers in the Venera series managed to touch down, but the extreme environment ensured they could only function for a few brief minutes. A rare astronomical event, known as the transit of Venus, occurs when the planet passes directly between Earth and the Sun, a spectacle that happens roughly 2 times each century. The transit of 1769 was a pivotal moment for science, as astronomers understood that by carefully timing Venus's journey across the solar disk, they could calculate the distance to the Sunday. This single measurement would, in turn, provide the foundation for much more precise methods of celestial navigation. In 1961, the Soviet Union initiated its Venus exploration program with the launch of Venera 1, the first probe sent toward the planet. Although it successfully passed Venus as planned, communication with the spacecraft had already been lost by mission control. The following year, NASA made its own attempt with Mariner 1. The mission was cut short when a coding error caused control issues with the launch vehicle, forcing its destruction just minutes after liftoff. Because the orbital mechanics for a Venus mission allow for convenient launch windows only every 18 months, NASA had prudently prepared a second probe. This backup, Mariner 2, was fundamentally a Ranger-class spacecraft that had been originally conceived for missions to the Moon. In these early years of the space race, the United States felt immense pressure to match the Soviet Union's achievements, which meant development timelines were incredibly short, leaving the Jet Propulsion Laboratory without enough time to build its intended, more advanced design. Mariner 2 began its journey in August of 1962. While every one of the Ranger spacecraft launched toward the Moon had previously failed, Mariner 2 was operational as it headed for Venus. However, its transmissions were faint, and a launch anomaly had sent it slightly off its intended path. After a week of travel, ground controllers sent a complex series of commands for a course correction. About an hour later, the spacecraft flawlessly executed the instructions, which involved a precise sequence of a roll turn, a pitch turn, and a final burn of its main engine. The probe's challenges were far from over, as several days later it lost its lock on both the Sun and the Earth, its 2 critical reference points for attitude control. It managed to reorient itself before engineers on the ground could even determine the cause of the problem, but a short circuit in one of its solar panels then left the spacecraft with dangerously low power. At this point in history, both the United States and the Soviet Union had sent probes toward the planets, but not a single one had yet achieved its mission. Mariner 2 seemed to be following a similar path to failure, as it lost several telemetry sensors and its internal temperature began to climb. Yet, as it limped onward toward Venus, some of the spacecraft's issues began to resolve themselves in unexpected ways. As Mariner 2 drew nearer to the Sun, the increased solar intensity meant it could operate effectively using just its one remaining solar panel. The probe passed just under 35,000 kilometers above the Venusian cloud tops, where its instruments detected no planetary magnetic field and registered temperatures across the planet approaching 500 degrees Kelvin. The data made it abundantly clear that any attempt to land on the surface would present extraordinary difficulties, but the flyby marked the first true American success in deep space. Mariner 2 became the first successful interplanetary probe, an achievement celebrated enthusiastically in California, the home of JPL. The next significant breakthroughs in the exploration of Venus would come from the Soviet Union, whose Venera series was focused on landing a probe on the planet's surface. The engineers designing the craft were aware that the surface temperatures were high enough to melt lead and that the atmospheric pressure was dozens of times greater than on Earth. The resulting landers they constructed bore a greater resemblance to deep-sea diving bells than to typical spacecraft. In June 1967, Venera 4 was launched, consisting of a carrier spacecraft and a separate spherical landing module. After entering the atmosphere, Venera 4's parachute deployed, and it transmitted data for 93 minutes before contact was lost at an altitude of 28 kilometers above the ground. Remarkably, its electronics had not been destroyed by the heat. It had simply exhausted its power supply. When scientists extrapolated from its final measurements, the results were staggering. A surface temperature of 500 degrees Celsius and a pressure of 75 atmospheres, conditions far more extreme than anyone had anticipated. In response, the Venera program fortified its subsequent landers and equipped them with smaller parachutes to accelerate their descent. Venera 5 and 6, launched in January 1969, gathered more information on the atmosphere's chemical composition, but neither probe survived all the way to the surface. The Venera series continued to evolve, with each mission refining the technology and incrementally extending the operational lifetime of the landers. A major leap forward came in 1975 with the launch of Venera 9, an entirely new design featuring an orbiter and a lander that worked in tandem, with the orbiter serving as a crucial relay station for signals sent from the surface. 4 months into the mission, the lander separated from the orbiter and, 2 days later, plunged into the atmosphere, while the main craft fired its engines to become the first probe to enter into orbit around Venus. The new lander was equipped with a ring-shaped shield that could function as a brake during its passage through the incredibly dense lower atmosphere. Venera 9 successfully sent back the first black and white photographs from the surface of another world, though a frustrating design flaw meant the lens cap on a second camera failed to eject. Just 3 days later and 2,000 kilometers away, its twin spacecraft, Venera 10, touched down and was hindered by the exact same malfunction. To survive the immense heat, both landers had been pre-cooled in space, and an internal circulating fluid system kept their instruments operational on the blistering surface for more than an hour. In 1983, 2 more Venera spacecraft reached Venus, outfitted with synthetic aperture radar. They undertook the first serious attempt to map the planet's hidden surface, and over the course of 8 months, they systematically charted the region extending from the North Pole down to 30 degrees north latitude. While NASA had played a more limited part in the initial surveys of Venus, a new era began in 1989 as the Space Shuttle Atlantis climbed into orbit carrying the Magellan probe. This spacecraft was set on a course for Venus, and much like the Venera missions that preceded it, Magellan's purpose was to use radar to chart the planet's unseen surface. It held the distinction of being the first interplanetary probe to be launched from the Space Shuttle. After a 15-month voyage through the solar system, Magellan arrived and settled into an elliptical path around its destination. To keep the mission's budget manageable, the probe had been cleverly assembled from a variety of spare parts that remained from previous NASA endeavors. Once some initial software challenges were resolved, it commenced its mapping operations. The images it transmitted back to Earth are still the most detailed, high-resolution views we possess of the Venusian landscape. These pictures revealed a world of low volcanic blisters and extensive lava channels, suggesting a surface shaped by intense geological forces. The planet's incredibly dense atmosphere acts as a shield, preventing all but the most massive meteors from striking the ground, which explains why so few impact craters were observed. Curiously, there was no clear evidence of the kind of plate tectonics that constantly reshapes the crust of our own world. After completing its primary mapping mission, Magellan adjusted its orbit to chart the planet's gravitational field. It found that on Venus, localized variations in gravity directly correspond to features on the surface, a characteristic not shared by Earth. A new and stark portrait of Venus began to form, one suggesting that its entire surface had been completely remade roughly 500 million years ago. Yet, for all the common signs of volcanoes and lava flows, Magellan was unable to find any definitive proof that volcanic activity was still occurring. That question would be taken up in 2006 by the European Space Agency's Venus Express, which entered orbit with a focus on the long-term study of the planet's atmosphere. Over its 8-year mission, the probe detected a significant increase in the amount of sulfur dioxide in the atmosphere. While this could have been caused by shifting wind patterns, it was also a potential signature of volcanic eruptions. Researchers additionally noted rises in infrared radiation emanating from 3 separate volcanic regions, offering more circumstantial clues of ongoing activity. The infrared team later observed short-lived temperature spikes that changed over periods of just a few days, strengthening the case that volcanoes on Venus may indeed remain active today. The mission concluded in 2015 after performing a series of daring dives into the upper atmosphere, which confirmed the presence of unexpected ripples in the mesosphere. Since Venus Express, direct exploration of the planet has been sparse. Though ambitious plans for future missions have been proposed, none have yet received funding. Venus, however, continues to be a crucial waypoint for missions venturing elsewhere. In 1974, Mariner 10 became the very first spacecraft to use the planet's gravity to alter its trajectory, an effect now known as a gravitational slingshot, on its way to Mercury. The maneuver, conceived by Italian mathematician Giuseppe Colombo, was a brilliant method for saving fuel and enabling multiple flybys of Mercury instead of just one. Today, this technique is a standard practice in mission design. 10 days after its launch, Mariner 10 was executing what should have been a routine course correction. The engine burn seemed to proceed without issue, but as the craft tried to reorient itself afterward, a problem arose. Mariner 10 determined its orientation by locking its tracking sensor onto the bright star Canopus. However, a tiny flake of paint that had detached from the spacecraft was interfering with the system. An automated backup procedure successfully reacquired Canopus, but the issue of flaking paint would persist for the remainder of the mission. Reaching Mercury requires a spacecraft to travel closer to the Sun, whose immense gravity poses a significant challenge. While voyages to the outer planets are continually slowed by the Sun's pull, a craft heading toward the inner planets is constantly accelerated. Mariner 10 skillfully used the gravity of Venus to decrease its velocity, allowing it to approach Mercury at a precise angle. Although it lacked the fuel to enter a stable orbit around Mercury, its path around the Sun was designed to allow for 3 close encounters. Its first pass showed a world that resembled our Moon, its surface heavily pockmarked with craters. Despite being the smallest planet, Mercury is the most dense, possessing a large, iron-rich core. One of the prominent features observed were large escarpments, such as Discovery Scarp, which cuts through 2 craters and has a cliff face 3 kilometers high. It is thought that these cliffs formed as the planet's core cooled and contracted. Mariner 10 was beset by ongoing technical difficulties. Its tape recorder had a tendency to stick, data transmission rates were restricted, and limited attitude control forced flight engineers to use the pressure of sunlight on the high-gain antenna and solar panels to help steer the craft. Nevertheless, the mission pressed on, ultimately managing to map about 45% of Mercury's surface, as the same hemisphere was illuminated by the Sun during each of its passes. Among its discoveries was a very thin atmosphere composed mainly of helium. Several months after its third and final flyby of Mercury, the probe exhausted its fuel and continues to orbit the Sun to this day. More than 3 decades would pass before the next mission to Mercury was launched. In 2004, Messenger began its journey, a probe designed specifically to achieve orbit around the small planet, a feat that came with a unique set of engineering constraints. It was equipped with a large, woven ceramic sun shield for protection, but for communications, It used an innovative phased array antenna that could be aimed electronically rather than a conventional dish. After a year in space, Messenger returned to fly by Earth, using our planet's gravity to adjust its orbit. Though not a massive spacecraft, it carried a powerful engine for making course corrections and for the critical orbit insertion burn. Its path then took it past Venus twice, each time using the planet's gravity to shed more speed as it fell deeper into the Sun's gravitational well. 3.5 years after it left Earth, Messenger made its first approach to Mercury, but its long voyage was not over. The probe had to execute 2 more flybys of the planet before it could finally enter into orbit, a milestone it reached after nearly 7 years in space. Throughout its mission, engineers faced the added complexity of constantly needing to keep the probe's sunshield oriented toward the Sunday. By being in orbit, Messenger was able to complete the global map that Mariner 10 had started decades earlier. The planet's defining feature is the Caloris Basin, an ancient crater more than 1,500 kilometers wide, though Mariner 10 could only survey part of it while the rest was in darkness. A map of the southern polar region uses color to illustrate illumination, showing how Mercury's lack of an axial tilt leaves deep craters in permanent shadow. It was in these very areas that the Messenger spacecraft uncovered substantial amounts of water ice. After several mission extensions, Messenger's journey concluded in 2015 when it ran out of fuel and crashed into Mercury. A new mission, Bepi Colombo, is now making its 7-year journey to the planet. This joint effort between JAXA, the Japanese Space Agency, and the European Space Agency is named for the designer of Mariner 10's trajectory. The Voyager 2 spacecraft remains the only probe to have made close approaches to the 2 ice giants, Uranus and Neptune, since it launched with its twin, Voyager 1, in 1977. The Voyager 2 mission was able to capitalize on an exceptionally rare alignment of the solar system's 4 outer gas giants, which allowed for close-up studies of each one. In 1986, the spacecraft made its approach to Uranus. The prevailing scientific theory suggests that a massive body must have struck the planet in the distant past, knocking its axis of rotation almost completely on its side. This extreme tilt means Uranus effectively has an east and a west pole, and for half of its long orbit, one hemisphere is bathed in continuous sunlight, while the other experiences a prolonged, dark winter. The planet is also encircled by rings, which are oriented along its unusual north-south equator. During its flyby, Voyager 2 made several key discoveries, including 11 previously unknown moons and a magnetic field that was significantly misaligned with the planet's rotational axis. The images captured by Voyager depicted Uranus as a surprisingly uniform and featureless world, but this placid appearance was likely a result of the particular season during its encounter. Subsequent observations using the Hubble Space Telescope have revealed that at other times in its orbit, distinct clouds and dynamic planetary weather do emerge in its atmosphere. The mission also provided the first detailed look at Uranus's largest moon, Miranda. Its surface is so fractured and chaotic that researchers initially proposed it must have been shattered by a tremendous cosmic impact, with the fragments later reassembling under gravity. A more current hypothesis, however, suggests that powerful tectonic forces, driven by the gravitational pull of Uranus itself, are responsible for the moon's jumbled and dramatic appearance. As Voyager 2 departed from Uranus, the backlighting from the distant sun illuminated 2 new, faint rings around the planet. The spacecraft was now on a trajectory toward Neptune, the final planetary target on its grand tour. In the 3 years it took to traverse the distance, engineers on the ground meticulously prepared for the unique challenges that lay ahead. Neptune orbits the Sun at a distance 30 times greater than that of Earth, and consequently, the intensity of sunlight there is only 1/1000th of what we receive. This faint illumination meant that long time exposures would be necessary for photography. Yet, Voyager 2 was traveling at such an immense speed that any long-exposure image would be smeared into a useless streak without a special solution. To overcome this, engineers developed a brilliant technique, calculating the precise rotational movements the entire craft would need to perform during each exposure to perfectly compensate for its forward motion and keep the camera locked on its subject. By June of 1989, Voyager 2 started sending back its first distant images of Neptune. Around the globe, there was a growing realization that the information returned by this solitary probe was fundamentally transforming our comprehension of the outer solar system. In an era before the widespread use of the internet, researchers at the Jet Propulsion Laboratory gathered around television monitors, watching intently as new data and images were painstakingly transmitted and rendered, line by line. Neptune presents as a more conventional planet than Uranus, with an axial tilt of about 30 degrees and a rotation in the same direction as Earth. While it is slightly more massive than its fellow ice giant, Uranus, its diameter is marginally smaller. An intriguing detail is that despite being farther from the Sun than its neighbor, Neptune radiates more heat. This indicates the planet has an internal heat source, which in turn drives more active and dynamic weather systems. Voyager 2 clocked wind speeds on Neptune exceeding 2,000 kilometers per hour, the fastest ever recorded in the solar system. The probe observed delicate cirrus clouds drifting in the atmosphere and captured images of a great dark spot, an enormous storm system analogous to Jupiter's Great Red Spot. This feature was identified as a massive anticyclone in the southern hemisphere, comparable in size to the entire planet Earth. When the Hubble telescope looked for this same storm in 1994, it had vanished, though a new dark spot was observed forming in the northern hemisphere. Voyager 2's final planetary observations were of Neptune's largest moon, Triton. A notable characteristic of Triton is its retrograde orbit, meaning it circles the planet in the opposite direction of Neptune's rotation. This is a strong indicator that it did not form alongside the planet, but was instead a captured object from the Kuiper Belt. As Voyager 2 moved past the planets and into the void, its cameras were switched off to conserve power for its continuing journey. Both Voyager probes are still traveling away from our solar system, measuring the influence of the solar wind as they go, and their mission remains the only one to have visited the ice giants. On January 19, 2006, an Atlas V rocket launched from Earth. It was an exceptionally powerful launch vehicle carrying an unusually small payload. This spacecraft, New Horizons, left Earth's orbit at a higher velocity than any probe before it, destined for the Kuiper Belt at the far edge of the solar system, with the primary goal of studying Pluto. Just over a year into its journey, New Horizons reached Jupiter, where it performed a gravitational assist maneuver that shaved 3 years off its total flight time. After its Jupiter encounter, the spacecraft entered a state of hibernation for most of its long cruise, sending back a simple all-is-well signal just once a week. It would take New Horizons more than 9 years to finally reach Pluto. In the time since the probe's departure, Pluto had been reclassified, losing its status as the 9th planet. The discovery of other objects of a similar size in the Kuiper Belt prompted the scientific community to formalize the definition of a planet, adding the requirement that a celestial body must have gravitationally cleared its own orbit. The features New Horizons revealed on Pluto were a source of profound surprise. This was not an inert ball of ice, but a living world, shaped by ongoing tectonic forces. The mountains, however, were not made of rock, but of water ice and frozen methane. Pluto also possesses a thin atmosphere composed mainly of nitrogen. The probe continued its flyby, observing Pluto's largest moon, Charon. Its icy surface is marked by deep canyons, and there is some evidence suggesting the presence of ice volcanoes. Charon is about half the size of Pluto, and the two bodies orbit a common center of gravity, tidally locked with one another. From the surface of Pluto, Charon would appear to hang fixed and motionless in the sky. As the New Horizons probes sped away from the Pluto system and into deep space, it began the slow, methodical process of transmitting all its recorded data back to Earth. At these vast distances, radio signals take 4.5 hours just to reach our planet, with the data arriving at a rate of only 1 kilobit per second. In total, it took 469 days for all the information from the Pluto encounter to be received. Early in 2019, New Horizons successfully flew past a trans-Neptunian object known as Ultima Thule, and with a mission extension, it continues to explore the remote outer reaches of our solar system. Earth is our home, and our natural environment is the product of a complex interplay between the sun, the oceans, and the atmosphere. The planet's polar ice and its tropical heat represent the extreme ends of our climate, but in the context of the solar system, this is an exceptionally narrow band of temperatures completely different from any other world we have observed. The remarkable stability of Earth's environment over geological time has allowed life to emerge, and in turn, life has fundamentally changed the planet. To the best of our current knowledge, Earth remains the only place in the universe to have given rise to life. The Orion Nebula is a vast cloud of interstellar gas and dust located within the constellation of Orion. It is a stellar nursery, a place where new stars are being born. As a portion of the nebula begins to condense, it breaks apart into individual clumps. Each of these clumps then contracts under its own gravity and starts to swirl, gradually flattening into a disk shape. These formations are known as protoplanetary disks, or proplids. At the center of a proplid, as the molecules are squeezed ever tighter, a fusion reaction can ignite, and a star is born. Some proplids that form near an already established star shine brightly, illuminated by their powerful neighbor. While this makes them easier to see, the stellar winds from the adjacent star are actively stripping away the glowing gas and dust. In contrast, dark proplids, which are observable only as silhouettes against a brighter background, are able to retain their surrounding ring of gas and dust as the system matures. The residual dust and gas left in the wake of stars provides the raw material for new planetary systems, a process the Hubble Space Telescope has observed so frequently that astronomers now recognize planet formation as a standard feature of the cosmos. Our own solar system began in just this way, some 6 billion years in the past, though the emergence of its planets was a much more gradual affair. Within the vast protoplanetary disk surrounding our young sun, tiny grains of material started to cling together, building up into larger bodies known as planetesimals. As these clumps grew in size, their gravitational pull intensified, which in turn accelerated their growth by attracting even more material. An early version of Jupiter is thought to have been the first planet to fully coalesce, its immense gravity sweeping its orbital path clean of debris. At its center was a core of heavy metals and rock, while its atmosphere, composed primarily of hydrogen, was compressed to incredible densities by the planet's own powerful gravity, burying any solid surface beneath thousands of kilometers of liquid gas. What we have learned from observing exoplanets has reshaped our understanding of this process, particularly the discovery of Jupiter-sized gas giants orbiting very near their parent stars. This has led astronomers to believe that the young Jupiter likely embarked on an inward journey toward the Sun, dragging a retinue of asteroids and comets along with it. However, Jupiter's migration was ultimately halted and reversed when it was caught in a delicate gravitational balance, an orbital resonance, with the newly forming planet Saturn. Not every object from this early era remained in a stable orbit around the Sun. Smaller bodies that passed too close to a planet were often flung away by its gravity, or, in some cases, captured to become moons. It is thought that as many as 20 smaller planets may have originally orbited in the inner solar system, their mergers and collisions eventually giving rise to the 4 terrestrial planets we see today. In this developing system, violent impacts were a common occurrence. Evidence preserved within the Apollo moon rocks suggests that one such collision between the proto-Earth and another planetary body was a pivotal moment in our world's evolution. A compelling piece of evidence lies in the composition of both bodies. Earth possesses an iron core that is disproportionately large, while gravitational measurements indicate the Moon's core is unexpectedly light. A collision between the two would elegantly explain this discrepancy, as the more massive Earth would have stripped away and absorbed much of the smaller body's heavy material. The impact was a glancing blow that sent the young Earth into a rapid rotation, creating a 5-hour day, and from the molten debris flung into orbit, the Moon that we know today gradually coalesced. While our Moon is not the largest in the solar system, what is remarkable is its mass in relation to its parent planet, a ratio greater than that of any other moon. This large relative size gives it a profound stabilizing effect on Earth's rotation over geological timescales. Without the Moon's steadying influence, our planet's axial tilt would vary by as much as 85 degrees, creating catastrophic climate instability. With the Moon, this variation is kept to a mere 1 degree. The final clearing of the solar system's debris occurred during a period known as the Late Heavy Bombardment, when the planets swept their orbits clean. During this time, the nascent Earth was relentlessly pelted by asteroids and comets, which delivered the vast quantities of water necessary for life. While the scars of this bombardment have long been erased from Earth's surface by active tectonic forces, the Moon, which endured the same onslaught, still bears the countless craters from that chaotic time. Once the turmoil of the solar system's formation had subsided, the young Earth found itself in an extraordinarily favorable position. Its distance from the Sun was perfect, allowing the planet's abundant water to exist in liquid form. As the Moon gradually drifted farther away, the planet's fast rotation slowed, allowing the Sun's warmth to be distributed more evenly across the surface. Furthermore, Earth's large, metallic core, combined with its steady rotation, generated a powerful magnetic field that extends far out into space, deflecting the charged solar wind and shielding the surface from the most intense solar radiation. In a universe often defined by hostility, the Earth had become a uniquely benign environment. The geological record reveals that around 2.7 billion years ago, a profound change began. Oxygen started to accumulate in the atmosphere. The vast iron ore regions of Western Australia are a testament to this era, formed as iron dissolved in the oceans reacted with the sudden abundance of oxygen to create iron oxide. This atmospheric transformation was driven by simple plant life, which used sunlight and carbon dioxide to survive and, in the process, released highly reactive oxygen as a waste product. This very waste product paved the way for more complex life to emerge, ultimately building an intricate web of plants and animals that completely reshaped the planet. The shift in atmospheric composition also had other dramatic consequences. Oxygen effectively stripped away many of the highly insulating gases from the air, causing the Earth to cool drastically and initiating a sequence of ice ages. Although there is abundant evidence for these cycles of planetary glaciation punctuated by warmer periods, the factors that trigger them are remarkably complex. The movement of continents, evidenced by ancient fold lines in rock, diverted ocean currents. Volcanic activity altered the atmosphere, and subtle changes in Earth's axial tilt relative to its elliptical orbit around the Sun all served as contributors to long-term fluctuations in the global climate. A precise way to study these past changes is through the analysis of ice cores drilled from Antarctica or Greenland, which contain a faithful record of the atmosphere stretching back 800,000 years. Within the ice, tiny bubbles of air, trapped between snowflakes long ago, can be accurately sampled. From this data, one pattern is exceptionally clear. During warm periods, carbon dioxide levels reach a peak of around 270 parts per million, while during the height of glaciation, They dropped to approximately 170 parts per million. Yet, from this data alone, it was difficult to determine whether rising CO2 caused the warming, or if the warming itself led to a release of CO2 into the atmosphere. In 1958, a scientist named Dave Keeling, working for the Scripps Institute, began a program of precise atmospheric CO2 measurements at the Mauna Loa Observatory in Hawaii. This marked the beginning of a unique and continuous dataset that would become known as the Keeling curve. Keeling's graph soon revealed a distinct seasonal variation, a rhythmic rise and fall that corresponded to spring and summer in the northern hemisphere, where the majority of the planet's land mass and plant cover is located. During the northern spring and summer, as photosynthesis increased, carbon dioxide levels would drop. By the 1970 seconds, however, a more disturbing trend had become unmistakable. Beneath the seasonal rhythm, CO2 levels were on a steady upward climb. At first, there was considerable uncertainty about what this might mean. The additional CO2 could trap more heat, leading to a warming phenomenon known as the greenhouse effect. Yet some scientists worried that a different factor, aerosol pollution, might block sunlight from reaching the surface, potentially resulting in a cooling environment. As the decades went on, different lines of evidence began to converge. Drill cores from the ocean floor showed that past ice ages had been triggered by Milankovitch cycles, which are long-term variations in Earth's tilt and its elliptical orbit. Though the direct effects of these cycles were minor, the correlation was obvious. The intriguing implication was that if such a small nudge could fundamentally alter the climate, then perhaps changes in atmospheric CO2 could as well. Scientists were beginning to realize just how poorly they understood the intricate workings of planet Earth. At the dawn of the space age, as scientists grew eager to make weather observations from orbit, America prepared a launch from Cape Canaveral, carrying a robotic weatherman into space. In 1960, the launch of Tyros-1 marked the dawn of space-based weather observation. As the first satellite of its kind, it carried 2 television cameras that sent back regular images of global cloud patterns, providing meteorologists with an unprecedented view of Earth. This mission was followed by improved versions. And because these early satellites occupied highly inclined, low Earth orbits, the data they gathered covered the entire planet and was shared around the world. This collaborative spirit was not new, building on a foundation laid in 1873 by the International Meteorological Organization, which in 1951 became the UN's World Meteorological Organization, headquartered in Geneva. With a UN resolution calling for peaceful uses of outer space, the coordination of different nations' weather satellites for the benefit of all humankind soon followed. The Nimbus program, which began in 1964, comprised a series of 7 satellites that served as a testbed for new technologies. Beyond just clouds, Nimbus collected data on other parts of the Earth system, including the atmosphere and sea ice. In this pre-digital era, all electronic image data was preserved on 70mm film, and the concept of establishing a permanent archive for future reference had not yet emerged. The Nimbus program was an early example of Earth observation, representing a shift beyond simple weather monitoring. Meteorologists began to see the planet differently, not as a set of isolated components, but as a single, complex, and interconnected system. Today, a dedicated fleet of satellites constantly monitors the atmosphere, the oceans, the ice, the land, and the biosphere. It is now understood that ice, particularly sea ice, plays a crucial role in the climate system. Polar ice flows slowly toward the coasts and melts, creating a source of cold water that drives ocean currents. These currents are vital, transferring heat from the equator to the poles and moving nutrients essential for life. Global winds also circulate water via clouds, which keeps the land moist enough to support vegetation. Plant life, both in the oceans and on land, removes CO2 from the air and replenishes atmospheric oxygen. The planet's ice, known as the cryosphere, along with its clouds, reflects a portion of the Sun's energy back into space. The extent of this ice and cloud cover is therefore an important factor in Earth's energy budget. As ice melts, it exposes darker ocean or rock that absorbs more solar energy. Similarly, the presence or absence of cloud cover affects the land or sea beneath it. Vegetation is also a key climate factor, with land plants pumping huge amounts of water vapor into the atmosphere. But things are changing. Humanity, simply through its sheer numbers, is influencing key elements of the planetary system. In just 50 years, the Earth's human population has risen from just over 3.5 billion to 7.7 billion today. More people need more resources, and while revolutions in agriculture and technology have occurred, the Earth's reserves are not limitless. In 1979, Europe began launching its own spacecraft. While these new Earth observation satellites were revealing changes, scientists were reluctant to reach conclusions about long-term trends. They understood that a certain amount of variability is natural to the planet's climate cycle, and though the steady rise in atmospheric CO2 shown by the Keeling curve was known, researchers sought additional, solid evidence that change caused by human activity was happening. The basis for one critical piece of evidence had been known since 1913, when spectroscopy revealed a layer of ozone in the stratosphere that blocked harmful UV sunlight from reaching the ground. In 1974, a postdoctoral fellow named Mario Molina published a paper which suggested that a family of industrial chemicals known as chlorofluorocarbons, or CFCs, could damage this protective ozone layer. The confirming evidence emerged during the 1,980 seconds from the work of meteorologists in Antarctica. The polar vortex above the southern continent was found to concentrate CFCs in the stratosphere. Here, mother-of-pearl clouds contain ice crystals which, in combination with ultraviolet light, split chlorine from the CFC molecule. Each single chlorine atom can then break down over 100,000 ozone molecules. A large area centered over Antarctica showed almost no ozone, and it became known as the hole in the ozone layer. The United Nations initiated talks to limit the production of CFCs, leading to the 1989 Montreal Protocol. This international treaty capped production and ultimately resulted in a 10-year phase-out. All countries signed the agreement, and the Montreal Protocol is seen as a model of international cooperation. In the 1,980 seconds, an upward trend in global temperature averages was also becoming clear. A scientific consensus emerged that the burning of fossil fuels was altering the balance of gases in the atmosphere. Most of our planet's fresh water is locked in the polar ice caps, with 61% of this ice covering the Antarctic continent. In the north, Greenland is also covered by an ice sheet. While there is no landmass at the North Pole, a large area of sea ice grows and shrinks with the seasons. Seasonal sea ice also fringes Greenland and Antarctica. Ice shelves are a third manifestation of polar ice. These are thick layers of ice that extend into the ocean from the mouths of glaciers, from which icebergs periodically break away. These regions are important to the circulation of global winds and ocean currents. Since 2002, NASA has tracked the prevalence of water and ice via the GRACE satellites, which were recently replaced by a similar pair of GRACE follow-on satellites. The two satellites follow the same orbit, and minute changes in the Earth's gravitational field cause them to change speed, creating a variation in the distance between them. This data is accurately measured, allowing researchers to record changes due to variations in groundwater or in ice thickness. During the life of the first GRACE mission, Greenland lost 285 gigatons of ice per year on average, while Antarctica lost 137 gigatons per year. From 2005 to 2016, sea levels rose by 3.7 centimeters, due to both melting ice sheets and the expansion of seawater. The continuous monitoring of sea levels from space has been underway since 1992, beginning with the Poseidon satellite and continuing with the Jason series of missions. Space-based observation has provided a crucial, long-term record of our planet's oceans. The Jason 3 satellite, for instance, employs a precision radar altimeter to chart both regional and global variations in sea level. The data reveals that in the 2 decades leading up to 2014, the average global sea level rose by 6 centimeters, though this increase was not uniform across the globe. Visualizations of this data show the greatest rise in red, with white areas indicating no change and blue sections signifying a decrease. What becomes clear is that the ocean's surface is naturally uneven, a result of the complex interplay between currents, the Earth's rotation, and the topography of the seafloor. All of these variables must be carefully factored in to establish a reliable baseline from which to measure change, such as the observed shifts in the Gulf Stream, visible as blue areas in the Atlantic. A compelling example of these changes can be seen on the ground in the Camargue region of southern France, a low-lying delta at the mouth of the Rhône River. Although a seawall was constructed there in the 1980 seconds to hold back the Mediterranean, the coastline has retreated by several hundred meters over the last 30 years. The scientific consensus is that a warming global climate is the primary driver, fueled by our reliance on burning fossil fuels. This activity has released an excess of carbon dioxide into the atmosphere, which in turn traps heat. An astonishing 93% of this trapped heat has been absorbed by the world's oceans. Data gathered by the Argo network of oceanic buoys indicates an average warming of 0.9 of a degree Celsius since the 1950 seconds. While that number may seem small, meteorologists understand its profound impact, as warmer sea surface temperatures directly fuel the intensity of hurricanes and cyclones, bearing out early predictions of more powerful storms. This trend is reflected in broader climate patterns, where long-standing weather records are now being broken with increasing frequency. In 2017, a consensus was reached by NASA, NOAA, and the UK Met Office, all confirming that 2016 had been the hottest year ever recorded globally. A more striking statistic reveals that 16 of the 17 hottest years on record have all taken place since the year 2000. Both NASA and the European Space Agency have been monitoring atmospheric CO2 concentrations and distribution since 1992. A visualization using data from 2006 illustrates the yearly ebb and flow of both carbon dioxide and carbon monoxide. While the majority of CO2 originates from the populous Northern Hemisphere, much of the carbon monoxide is generated by seasonal fires in Africa, Australia, and South America. These increased atmospheric CO2 levels are also linked to other unfolding consequences, such as prolonged droughts and more severe forest fires. Such events release an enormous pulse of greenhouse gases, creating a feedback loop that magnifies the underlying problem. Through its Copernicus program and Sentinel Earth observation satellites, the European Space Agency has committed to making climate information freely accessible to policymakers, businesses, and researchers. ESA's Director of Earth Observation Programs, Joseph Ashbacher, explained the long-term context using a graph of CO2 concentrations over the last 800,000 years. He noted the natural fluctuations corresponding to ice ages and warmer interglacial periods, but pointed to a crucial threshold. For all of that immense history, he reported, atmospheric CO2 levels never rose above 300 parts per million. Then, beginning in the last century, the value began a steep ascent, climbing toward 400 parts per million and beyond. Despite this data, the recent COP25 climate summit in Madrid yielded little progress on a unified international agreement to reduce greenhouse gas emissions. The challenge is that while some economies and businesses will need to adjust, that task grows more difficult with each passing year, and eventually far greater adjustments will be forced upon everyone. the Earth remains the only place we know of that harbors life, and the stability that has allowed this intricate web of life to flourish is remarkably fragile. The benign environment we depend on is a result of the complex interactions between the countless creatures with which we share this world, underscoring the profound importance of looking after our planetary home